So far, our study of random mechanisms for networks has focused on building up graphs. And now in this video, we're going to talk about the kind of the opposite, which is we will use random process in order to remove or destroy a graph. And so this is typically given the name percolation. And so we can talk about node or edge percolation. And it really just refers to removing a certain fraction of the nodes or of the edges. And so depending on what the network is and what you're modeling, it could make sense to remove nodes or edges. In a power line network, maybe edges fail, the power lines are cut, and so that would mean edges are removed. In the essentially the router network of the internet, you could imagine that computers are attacked or maybe have some sort of denial of service attack or maybe they just fail, in which case they essentially are removed from the network and no communication can actually happen between any of its neighbors in that node. And so effectively that node is removed as soon as it shuts down. So like I said, failure or this process of removal can represent kind of bad things, such as death in a population, destruction of like power lines or properties or failures of equipment. But it doesn't always have to be a bad thing. Depending on what we're modeling, the process could be a good thing. For example, one of the classic ones is that vaccination effectively removes people from a network that's modeling the propagation of an infection or a contagion. In the context of percolation, oftentimes it's characterized as an occupation probability. And to be honest, this seems a little bit reverse what I would naturally define. But the idea is that when this phi probability is 1, then no nodes are affected by the process. So nothing is removed or no edges are removed, and all occupied nodes or edges are completely functional. When this probability is reduced down to 0, that means the process, this random process, has now affected everything. So either all the nodes or all the edges. And so then the interesting part is not necessarily at these two extremes, but somewhere in between. And so it's somewhere in between. What we observe is at some point in time, assuming the network kind of started off as a giant chunk, at some point in time, we cross what's called the percolation threshold, at which point we no longer have a giant component. So you can imagine that we studied the giant component in the context of Erdos-Renyi graphs, and there, as the probability increased or the average degree increased, all of a sudden the giant component formed. And so that was a relatively quick process, a relatively sudden change in terms of the size of that component related to the probability or the average degree. And now what we're saying is kind of the reverse. As we now go backwards on that curve, we lose that giant component in the same way. And so just as an example, we can imagine this being our percolation threshold. And for the good cases where if we don't vaccinate enough, then we get an epidemic. So that means that essentially the network is completely connected still, and so the contagion can naturally spread. But if we manage to essentially poke holes in the network in enough places using vaccinations, then the disease is going to be confined to some smaller component of the graph that is kind of isolated. So it's really about essentially what are the remaining components after you remove some of the nodes or edges. In the internet, if we start removing nodes, then it's possible that at some point in time, the communication can no longer reach each other. So for example, we may lose connection with Australia and no longer be able to send communication back and forth. Whereas if you were still within that percolation threshold, even if you lost some nodes, there would still be the opportunity to actually communicate across the network because there's redundancy of paths. So one of the interesting things, and this is going to be the topic of a paper you'll be reading, is that this percolation, we can think about that as being a random process. So it mimics maybe failures that might happen, but they can also be actually strategic or attacks. And so that means that we could choose specific properties about nodes or edges or different other characteristics about the network to target certain nodes for removal first. So instead of doing that process randomly, we could pick, for example, one of the most important nodes and remove that first. And so one of the first proxies of doing that would be doing that by degree, but there's certainly many more ways in which one could do that. The configuration model, this is something we won't get a chance to go into too deeply, but if you want to, you can certainly come back and look at this, that the configuration model gives a very nice analytic framework for understanding a lot of properties about percolation process. And one of the final things that's worth noting is when we look at percolation in a real network, we actually have to execute a program that essentially emulates the random process or the targeted process in which nodes or edges are removed. So if we're looking at a random process that we can think about, remember that we have this phi probability that represents the probability of any node or edge being removed. So let's just talk in the context of node removal. Phi represents the probability that any node is removed. It's a uniform probability. And so if you were to try to emulate what happens as the network is slowly dissolved, essentially as we remove more and more nodes, that would essentially mean that the percolation probability would gradually decrease. So we'd start at 1 and then we'd gradually go down to 0, and that would mimic the dissolving of the graph. But at each point, at each choice of phi, at 0.9, then 0.8, then 0.7, we'd need to do a process where we actually flip all the coins to determine whether or not the nodes have failed or not. And that process is a little bit computationally heavy compared to one of the alternatives, which, and it actually is not only computationally nice, but it's also kind of intuitively nice, is to, instead of think of this probability phi, we can think about this number of nodes R that are occupied. So remember, occupied means functional. So those are the ones that still work. And so the idea here is that if we could figure out a way of counting these, then that actually makes it a lot easier. And so the reason why that is because if I wanted to remove 10 nodes, and I want to see what the network looks like after that, how many components there are and how well connected the network is at removing 10 nodes, or say 10% of the nodes, then when I move to 15% of the nodes, I don't have to remove all 10% all over again. I don't have to flip all those coins. I've already flipped those, and so now I just need to add 5 more. And so adjusting the components and identifying components when you remove one node at a time is a lot easier than if you have to essentially flip all of the coins as if you were using this probability. So it's this idea that you don't have to do as many versions of breadth first search because you have a certain component decomposition of your graph at when you've taken R nodes. When R nodes are occupied, and then you're going to reduce that, and you're going to reduce that only by one node, and so it's pretty easy to update the clusters or the components that you already have kind of stored away. So what makes that possible is the fact that we can express the expected size of the largest component, so the biggest component as a function of this occupation probability. We can actually express that in terms of the expected size of the largest component as a function of the number of nodes that are occupied. And so one way of connecting the number and this probability is, again, it's equivalent to coin flips. Here we have R successes, which means that we have R occupied nodes, and then we also have the total number of coin flips that we're going to make is the number of nodes, because we're emulating node failure in this case. And we're going to flip are of them. So this looks very much like the ER degree distribution, or the ER degree distribution. So what we're able to do then is then express this expected size. So this is in terms of phi, but now we're going to express it in terms of expression over R. So if this is the probability P of R, then what we're going to do is just multiply this probability distribution in terms of R by the expected size. And so SR is something that we would measure through experiments, and then that would be able to, once we substituted this in, we'd know SR, and then we'd know this distribution, and so we would be able to calculate this S of phi. So then we'd be able to evaluate, okay, so what is the largest size that we expect given a certain probability of occupation, not based on what we're counting, which is the number that we're counting. And a topic that isn't covered in the reading is, but a very important one in the literature, is this concept of cascading failures. And so everything that we've talked about percolation so far is kind of independent events. Cascading failures is the idea that one failure can lead to essentially future successive failures. And so power grids is a very common one. You could imagine traffic also has very good examples. And these the successive failures are often linked to essentially breaching capacities. So for example, in this example here, that we have 8 units, say, of power that's going to be distributed through a power grid, and certainly this edge here can contain all 8 units. And then those 8 units then need to split between these 3 edge weights. But if you look at that, the sum of those 3 edge weights is still 10, and so that still can manage to capture all 8 of these units. And then again, once this has moved past these 2 nodes, we can again see that 7, 5, and 5 lead to 17, which is even more capacity, and so there's no problem with transferring these 8 units from this target to, or from this beginning source node to this target. If we have a failure in a link, so for example, if this edge fails, then we lose capacity in the overall graph. And so this is certainly connected to the idea of cut sets and max flow. And so in this case, if 8 units is getting pushed through, this first link is still fine, but as soon as it gets split into these 2, now we only have 5 capacity. And now that means that these edges are beyond their capacity, and so they then successively fail. And so that would be the end. Now this section of the graph is completely disconnected from this section of the graph. And so that's the idea of cascading failures. Clearly in a larger network, this could have essentially iteration after iteration where successive edges fail. So what you would have to do is you'd have to make sure that you increase these edges in order to make sure that you'd need to make sure that the edges could actually contain the units that you're trying to pass through.